Hi everybody, welcome back from spring break. Today I am going to go over a little bit of a brief review of what we've done so far in the semester and then the expectations for the Lab 4. So Lab 4 is going to have one section using a new data set, electric.xls from the Coop textbook, and then the second part of it is going to incorporate dummy variables for the first time. So it's going to review everything we've done so far as we build into incorporating dummy variables. It's only going to, it's only going to look at using dummy variables alone and with traditional quantitative variables. We're not going to do interaction terms yet. We're going to lecture on that first, and then we'll have that lab later on down the road when we look at other stuff. So what we want to remember as we get into this is that we are looking at OLS regressions, ordinary least squares regressions, which means we're looking, that was from last time, right there. We're looking at finding a line of best fit through a data set, right? We have a sample of data from a population, and we're trying to find a best fitting line through that set of data to help describe the relationship between our dependent variable y and our explanatory variables. We started out with just one explanatory variable, x, that had a coefficient beta attached to that x that describes the nature, the marginal effect of x on y, and a constant a that we don't worry about too much. And there is a x value for every y value in our sample, and our statistical software uses that relationship between the actual x's and y's to calculate or to estimate an alpha hat, a beta hat, and a y hat using our sample data. We then expanded to say, well, what if we had more explanatory variables? And then the newest thing we said was, what if we had more kinds of explanatory variables instead of just quantitative variables like acres of lot size or years of age or numbers of bedrooms or percent of forest loss? What if we had something like whether a country is a democracy or not, or whether a house has a driveway or not? And so what we have now is this new system where our regression equation has y equals alpha plus beta 1 d1, beta 2 x1, beta 3 d2. And so that could be for the H price or the home price data set, we could be looking at how a house's sale price is influenced by whether it has central heating or whether it has air conditioning or not, what its lot size is, and whether it has a basement or not. We can imagine other examples, things like whether a person, what a person's wages are could be a function of whether they finished college or not, how many years of experience they have, and whether or not they are a naturalized citizen, something like that. Either way, we have our normal quantitative variable here, which means it's some number, and then we have our dummy variables here, which means they're either 0 or 1. And it's going to be defined in the data set whether that is the yes or the no. Usually it's 1 is the yes. So that's what we're going to do with this data set, with this lab. We're going to start with the electric data set, which is at the Coop textbook website and posted on Canvas. And what that data set is it has for the dependent variable, for the y variable, output in cost of production in millions of dollars per year. So how much it costs in millions of dollars per year to produce. In this case, it's these are electric companies. The independent variables. So we have our dependent variable y that depends on our model, right? And that is the cost in production in millions of dollars. The independent variables, our x variables, our explanatory variables, are going to be kilowatt hours per year of production, labor costs, the price of labor in dollars per worker per year, and the price of capital in dollars per worker per year, and then the price of fuel used to generate that electricity in dollars per BTU. And this is a data set that contains data for 123 electricity utility companies. So that's a new data set. We've never worked before, but we're doing super, super traditional things with it, just multiple regressions, nothing funky. And then the next data set we'll use is going to be that home price data set. And that's where we'll get into a little bit of dummy variables. So let's get started. Okay, so here we are back in Stata. Remember, the first thing we want to do is go ahead and start a log file. I like to put my name and some identifying information in there. So I'm going to put in, put it in here. I'm going to say my name and lab 4 so that I can keep track. And that's going to go ahead and log everything I do. I could even put a little note here, lab assignment 4. You want to remember with those asterisks, it's going to change the text color to green and let you know that you are writing a note, not putting in a command. And then I want to go ahead and import my first data set. That first data set is going to be that electricity data set. So I'm going to pull that up. And that's electric.xls. And oops, I forgot one of the problems with this data set. I'm going to go ahead and cancel that because I've had this problem before. So that electric data set, you see it's got 2 levels of variable names. And so you're not going to be able to import it because there's the variable name and then it has the units below it. That's going to make it hard. So actually, let me go back and show you guys one more time and talk about it while we do it. So if I go in and try to upload that first electric data set, it's going to see here, if my first row is the variable name, cost, output, price of labor, price of capital, and then over here we have price of fuel. But the second row is the units. So hundreds of thousands of dollars, thousands of kilowatt hours, dollars per hour per year, dollars per year, dollars per million BTU. The problem is, if I go to import the first row as variable names, I still have these units in there, and that's not going to, Stata's not going to like that. Stata's going to say, hey, wait, that's not a number variable, that's something wrong, and it's not going to like my data set. I'll show you. It'll import it with some arrows. When I go to summarize my data, I'm going to get no observations. And you can look at the data editor and see it went to read this first line of data and said, whoa, what is that? And completely shut it down. So I'm going to clear that out. And instead of importing the original data set, I'm going to import this electric 2, which I used where I already took out the units. So now it works. Now my first row is variable names. The second row where there are the units is removed. And so we don't have to worry about it. Now it'll import perfectly fine. And I can summarize my data again. And now I see I've got 123 observations, 123 electricity utility companies. The mean cost is $400,000. And the output in kilowatt hours, the price of labor, the price of capital, and the price of fuel to produce those kilowatt hours. And so that is the data set. So the first thing the assignment asks us to do is to run a regression of y on x1, which is that kilowatt hours of labor, or that kilowatt hours of output. So I'm going to run a regression of cost on output, how much the firm produces, and we get a pretty great regression result here, right? So our coefficient is pretty low, but remember, this is thousands of kilowatt hours, and the marginal effect of an additional 1,000 kilowatt hours on hundreds of thousands of dollars of cost. What we can see here is that even though the coefficient is low, this is still a pretty big number because it's it's an increase in hundreds of thousands of dollars of 0.004 hundreds of thousands of dollars. Does that make sense? Kinda. Let me say it a different way. Sorry, not hundreds of thousands of dollars, millions of dollars, millions of dollars. And if you have confusion about this stuff, if you go back to, I believe it's chapter 4, the introduction to simple regression, they'll go through these data sets and talk about the units and the interpretation for all of these different data sets. And that's really, really helpful, I think. But what we can say is that when we're dealing with this data set, we have a our dependent variable is y is, let's get this out of here, y is cost in millions of dollars. And our x is output in thousands of kilowatt hours. So if our beta hat is 0.00478, or we could round it to 0.005, what we're really saying is each additional 1,000 kilowatt hours of output is going to tend to increase cost by $4,780 or $790, depending on where you round it. Does that make sense? Hopefully. Okay. If not, let me know. We'll talk about it in the discussion thread. You can, again, reference the book. It's on, let me see, hold on. They talk about this in chapter 4. In the examples 4.2a and 4.2b, they go over this electricity set, and so they really review it in really clear ways. And in 4.2b, they talk about the interpretation of the coefficient and say, okay, if this is the coefficient, this is how you interpret it given the scale of your variables. And so that's why it's important to remember the scale of your variables, right? So that's how we would interpret this. So each additional 1,000 kilowatt hours of output will tend to increase the cost of running an electricity utility company by, 4,700 and I'm going to say, let's just do it all, $886 or almost $5,000. Sound good? We can also interpret our R squared. That should be a little bit more familiar and easy. Our model, tends to explain 91% of the variation in firm costs. So what that's saying is we can explain more than 91% of the variation in costs that electricity utility firms face just by looking at how much electricity they produce, how much output they generate. Makes sense. We can also check the F-stat and the p-value for the F-stat for our R squared, and we can reject the null hypothesis. That's a big S-stat, very small p-value. And we can do the same thing for output. We have our coefficient here. Our standard error is less than half of our coefficient. Our t-stat is large, and our p-value is below 0.05, so we can reject the null hypothesis at the 5% significance level. And here we have our confidence interval that does not contain 0, so we are 95% confident that the true value of beta falls within that window. So that's what you want to say, right? Interpret the results. Let's say we can reject the null hypothesis for both the coefficient and the R squared because both have p-values equivalent to 0. The next part of the problem asks me to run a regression with all of the explanatory variables and then see how that looks. So I'm going to now run a regression with cost, output, the price of labor, price of fuel, price of capital, price of fuel. And so we're putting in more explanatory variables. We expect that to give us more explanatory power, right? What do we get? We get a slightly higher R squared. Now our model explains 94.3% of the variation in firm cost. But we've got a couple of issues over here. Not terrible. The p-value for the price of labor is a little bit, it's small enough. It's small enough. We can reject the null hypothesis at the 5% significance level and at the 1% significance level. The price of capital is not super strong, and that's the p-value is borderline at the 5% significance level, and we couldn't reject it at the 99% confidence interval and the 99% significance level. So that's a little bit borderline, but otherwise everything's pretty good. We see that the coefficient for output has gone down from 0.004788 to 0.00473. So now each additional 1,000 kilowatt hours of production is going to increase cost by a little bit less, by $4,731, give or take. The price of labor has a really small effect on cost, as does the price of capital, and even the price of fuel on the margin has a pretty small effect relative to what we might expect. But it does make sense that the price of fuel is going to be pretty closely tied with cost, because if we think output has such a big role determining cost, then the cost of generating that output should have a big role to play. So we can go ahead and interpret all of our explanatory variables. We can talk about what is surprising or what is not surprising. We can go ahead and reinterpret our output variable. So each additional 1,000 kilowatt hours of output will tend to increase cost by $4,731, holding the price of labor, price of capital, and price of fuel constant. And that's the one thing that's different about a multiple regression analysis relative to a simple regression, is we want to remember that when we interpret our coefficients, we're holding everything else constant. So I could also say each additional dollar of labor costs per year will tend to increase the cost of production by 36 or $3,600, holding all other variables constant. Okay. The last thing we want to do is run a correlation matrix of all the variables, and this is going to be our check for multicollinearity. So we can see here cost and output are very closely correlated. That's good. That's why we got an R squared that was so high. We see that price of labor, price of capital, and price of fuel are not as heavily correlated. And if we wanted to pick something that might have a multicollinearity problem, what we'd want to do is look at the variable that has the highest correlation. And here we see price of labor and price of fuel are pretty positively correlated. And if we go back, we see that price of labor was a little bit problematic. Price of capital was more problematic, but really nothing here stands out as something we have to cut out of our regression. And so even though there's a pretty high correlation here, we probably don't need to kick anything out for multicollinearity, but it's a good way to check. And we want to remember multicollinearity is when two variables are trying to explain the same thing. It's a problem of having too many variables, whereas the omitted variable bias is a problem of not having enough. So that's our review. Next part, we want to go ahead and clear this out and add in the home price data set. I'm going to import that, and we're going to look at dummy variables for that. Okay, so we're super familiar with this data set now, and what we're going to be looking at are sale price, lot size, bedrooms, bathrooms, stories, driveway, rec room, and aircon. So let's go ahead and start with running a regression of Y on driveways and air conditioners. And if you need a review, these are examples in the book, example 7.1, C, D, and E in the textbook. These are also examples that we went through in the slides. You can go through and check there too. I'm going to go ahead and do that. So we're going to do driveway and rec room. So sum real quick just to see what our variables are. Good. And now I want to run a regression of sale price on, that was driveway and rec room, right? Yep, D1, D2. Okay, perfect. And remember, when we have these dummy variables, what we're doing now is we're saying basically there are 4 kinds of houses. We have, oops. There is a house that has D1 equal to 0 and D2 equal to 0. There's a house that has D1 equal to 0 and D2 equal to 1. There's a house that has D1 equal to 1 and D2 equal to 1. And a house that has D1 equal to 0 and a house that has D2 equal to 0. And so that's what we're going to see. We're basically looking at 4 equations because these are going to be either 1 or 0, and so there's not a marginal effect. So let's think about it this way. How would we interpret the coefficient for driveway? It's not miles of driveway, it's just whether a house has a driveway or not. The coefficient is 21,159.91, which we know is in dollars of sale price. So a house that has a driveway will tend to see the sale price increase by $21,159.91, holding rec room constant. So that's how you want to remember to interpret that. So we could also say having a driveway will tend to increase a house sale price by, and in these cases, it's really good actually to round, because when you use too specific a coefficient, it gives a false illusion of certainty. We're not certain that it's 21,000. Look at our 95% confidence interval. Our 95% confidence interval says we're 95% sure it's somewhere between 15,000 and 27,000. So that $159.91 is a false sense of certainty, right? So it's fine to interpret it with a little bit of a rounded number because we don't know for certain, right? Having a driveway will tend to increase a house's sale price by $21,000. We can also interpret rec room as saying that the presence of a rec room or a house with a rec room is going to tend to sell for $16,000 more than a house without a rec room. We could say that, we could also say that a house with a rec room and driveway will tend to have a sale price of $47,000 plus $16,000 plus $21,000, right? Because if we think about this, if we have a house that has D1 equal to 0 and D2 equal to 0, then we know that Y is going to be equal to alpha, which is $47,099, plus beta 1 times D1, which is going to be equal to 1 in this case. So that's going to be $21,000, plus beta 2, which is equal to 1. So it's going to be $16,000 times 1. Gives us this home's sale price. So that's 47, 68, 70, $84,000. What did I say now? 47, 50, 68, 80, 94,000, right? $47,000, 4, 5, 6, 7, 8. Okay, $84,000. There we go. That's why you don't do math in your head on camera. So those are some ways we can interpret that. I definitely should have put an asterisk in front of that, but that's okay. And then we can interpret the R squared. Again, this model explains very little of the variation in sale price. We can reject the null hypothesis for our betas and for our R squared. Even though our R squared is really low, it's still significant. And so you can say some stuff about that, about the p-values, the confidence intervals. You can interpret the value of a house with no driveway and no rec room. That's going to tend to have a price of $47,099, right? The next move we want to make is to go ahead and run a regression of Y on air conditioner and lot size. So let's do that. So we got sale price, lot size, and air conned. We get R squared of 40. Our model tends to explain 40% of the variation in sale price. I'm going to start cheating because I'm running out of time here. Each additional square foot of lot size will tend to increase house sale price by $5.60 regardless and then here, the presence of air conditioning is going to tend to increase the sale price by about $20,000. And in this case, we're going to be holding lot size constant. So what we're saying here is that having an air conditioner will tend to increase a house's sale price by $20,000, holding lot size constant. So if two houses have the same lot size, but one of them has air conditioning and one of them doesn't, we're going to expect to see a difference in sale price of about 20 grand. Okay? Again, we can reject the null hypotheses because our p-values are nice and low. They're below the 5% significance level. Our t-values are high. Confidence intervals don't contain 0. We can look at the model or regression sum of squares here, the residual here, and the total sum of squares. And that gives us another measure of our model's Success. Last part, part C. Run a regression of y on D1, D2, X1, X2, and interpret the R-squared and results. Make sure the results are statistically significant. So we're going to be looking at sale price, a regression on sale price and driveway, rec room, lot size, and bedrooms. So let's do it. Reg sale price, driveway, rec room, lot size, and bedroom. Okay, first let's check for our statistical significance. P-values are all below 0.5, so we can reject the null hypothesis for each coefficient, estimated coefficient at the 5% significance level. Our F-stat is large, our p-value is low. Our R-squared tells us that this model explains about 42% of the variation in sale price. We can then start to interpret our coefficients. Having a driveway is going to tend to increase house sale price by $12,600. Having a rec room is going to tend to increase house sale price by $10,000 to $11,000, holding driveway lot size and number of bedrooms constant. Each additional square foot of lot size is going to tend to increase the sale price by $5.20, holding number of bedrooms, presence of driveway, and presence of rec room constant. Each additional bedroom is going to tend to increase the house sale price by about $10,000, holding lot size, presence of driveway, and presence of rec room constant. Okay? And one of the things you want to think about when you're going through and interpreting these dummy variables is, again, how this creates multiple regression lines. So I'm going to move away from Stata for a second and talk about it on the whiteboard. So what we're doing here, I'm going to try and reduce the glare, is we are constructing a regression equation where sale price is now a function of two dummy variables and two qualitative variables. Right? So remembering that these dummy variables can only be either 0 or 1. That means that we basically have four kinds of equations. Given that the coefficient for driveway, and I'm just going to round these, it's going to make it faster and quicker for us. Think about the real values and the real variables if you want, and the enumerated values, but I think this will get us there faster. So we have our constant is negative 2,735. So we're just call it negative 2,700. Our coefficient for driveway is 12,600, I'm going to say. And I'm going to round the coefficient for rec room to 11,000. And the coefficient for lot size, $5.20. And the coefficient for bedrooms, 10,600. Oh, it's called 11,000. What that means is we now have a system of equations where if D1 is 0, then it's y equals alpha plus D1 falls away, and now if D2 is 0, it falls away too. It's just beta 3 x1 plus beta 4 x2. If these are both 0, these both go away. So if and only if D1 equals 0 and D2 equals 0. On the other hand, if we have D1 equals 0 and D2 equals 1, we have y equals alpha plus beta 2 D2 plus beta 3 x1 plus beta 4 x2. Try not to get bogged down by the alphabet soup here, because really what we're saying is there's a house now that has no driveway, but it does have a rec room. And so if there's no driveway, if D is equal to 0, no matter what beta 1 is, multiply it by 0, it goes away. And we just have beta 2 times 1, beta 3 times whatever lot size is, and beta 4 times whatever bedroom size is. If and only if D1 equals 1 and D2 equals 1. Then we have the full equation. If this is 1, this stays in. If this is 1, this stays in. So now we get y equals alpha plus beta 1 D1 plus beta 2 D2 plus beta 3 X1 plus beta 4 X2. And really what that would look like is $12,600 plus $11,000, so that's $33,600, minus 2007, so that's going to be, I'm not even going to try. I don't know where my calculator went. 12,600 minus 2,700 plus 11,000, $20,090, right? $20,900 plus 5.20 x1 plus 11,000 times x2. Does that make sense? Because these become constants if it's 1 or nothing if it's 0. If D1 is equal to 0, then beta 1 doesn't matter. If D2 is equal to 1, then beta 1 becomes another constant. And that's why we get a system of equations. So now let's do the last one. If D1 is equal to 1 and D2 is equal to 0, then our equation becomes y equals alpha plus beta 1 D1 plus beta 3 X1 plus beta 4 X2. Hopefully that makes sense, but that's how you want to think about interpreting these equations, understanding these coefficients, and moving forward. So let's wrap up the Stata section, and then we'll be ready to meet on Wednesday or on Friday and talk about this some more. Hold on. Okay, so here we are, back in Stata, and we can say things like each additional square foot of lot size will tend to increase sale price by $5.20, holding number of bedrooms, presence of driveway and rec room constant. Having a rec room will tend to increase sale price by $10,968, holding lot size, number, bedrooms, and driveway constant. Sound good? Start to make sense? Kind of remember it from a week ago, hopefully? Okay. Let me know what questions you have. Let me know what concerns you have. This has hopefully given you an opportunity to, to review what we've talked about in Stata, what we've learned, and get you refreshed and ready to get back into talking about regressions with dummy variables. Remember when you're done to close your log. Is that right? There it is. Log closed. Remember, you can always save your commands in a do file. So I can go ahead and say, I want to remember the command for sum. I want to remember the command for correlating a variable. Maybe I want to remember the command reg, sale price, lot size, and rec room, something like that. You can always put that in a do file. We're not going to use Stata files in this class, so when I go ahead and go to, now that my log is closed, I can go ahead and close out Stata. Oops. And it asks me if I want to save the data. I don't care. It's just that home price data set. I know where it is, so I don't need to save it. I'm done for the day. Okay? So that's it. Let me know what questions you have. Hit up Canvas discussion threads. I will see you all on Friday, April 2nd. Holy smokes. All right. Have a beautiful day. Thanks, everybody.